Good afternoon and welcome back to ARTtech seminar. My name is Natasha Trygg and I will be your host. Our next speaker is Paul Greenfell, who is going to talk about the retro demo scene coding. So, Paul, welcome.
Hello. My name's Evil Paul. I'm here to talk about retro demoscene coding, and specifically I'm going to talk about the ZX Spectrum. It's going to be kind of an introduction to demoscene coding on the Spectrum, so it's kind of a 101, just a kind of a basic overview. So when I started thinking about this talk, I had grand ideas about all the things I would introduce and talk about how the Spectrum works and all the different effects you can do and how to code them and how to optimize them. And I realized that was far too much stuff. So I've cut a lot of it out, and it really is kind of a basic overview. The idea is to kind of bootstrap you. If you want to write Spectrum demos, this should help you get into it and kind of show you the basics. So we'll start off with, what is a Spectrum? Some of you may not know. It was released in 1982. It's discontinued 10 years later. It sold over 5 million units. It was massive in Britain, in the United Kingdom. It was one of the first mass-market computers in the UK. Here in kind of Northern Europe and in America, you had the Commodore 64. We had the Spectrum. It's still kind of spread outside the UK, but it was mostly a United Kingdom computer. But it really helped to kind of create the UK games industry. There are so many programmers and, in fact, companies who kind of cut their teeth on the Spectrum, so it's massively influential inside Britain. The software was distributed on cassette tape, if you remember these. Somebody remembers them. And you had to wait 5 minutes for your game to load or your demo to load. No fast disks. So this is what the Spectrum looked like when it was released. These are the adverts for it. Ridiculously cheap, £125, and that was part of its appeal. It was very cheap compared to the alternatives. It started off with 16K of RAM, and then a bit later they released a 48K RAM version. It's still pretty small. And that's actually what it looked like. Very basic looking computer. After a while, they upgraded it, and you had 128K. This was kind of like the sweet spot of the Spectrum. This was the good model. They put more memory in it, and they put a proper sound chip in it. Previous models aren't so much use for demo scene coding, and the models after this don't really add too much. But they did add more. We had the glorious Plus 2, which has a built-in cassette recorder. Nothing else really added to it. And then finally, right at the end of the life cycle of the Spectrum, you had the Plus 3, which had a really bizarre 3-inch disk drive on it that was still pretty slow, didn't really have sort of massive take-up in the market. So let's start talking about the hardware and kind of delve into it. So we're going to talk about this particular one. This is the ZX Spectrum 128. This, as I say, this is like the staple. This is the platform that most demos and games are aimed at. I should point out at this point, it was also often called the toast rack. But you can see the grills down the side of the screen, down the side of the computer. I don't think they actually added anything other than they look cool in the 1980s. But people used to think you could put toast in them, so it was called a toast rack. And if you take the lid off, that's what it looks like inside. So remember I said it was very cheap? The reason it was very cheap is because pretty much all of the components were just off-the-shelf components. There's nothing really special in there apart from one chip, and that one chip isn't very special. So you have the RAM along the bottom, the audio chip, single chip, you have the ROM, you have the CPU, you have the video modulator and video circuitry up in the top left. The ULA is the only sort of custom chip, and we'll kind of delve into what those things are individually in a minute. But it's pretty much off-the-shelf hardware. So we start to delve in a bit now. We start with the Z80, which is the processor. It's an 8-bit CPU with 16-bit address bus, pretty standard for an 8-bit CPU. It's what we would these days term a complex instruction set. The instructions are not generalized instructions. There's between 1 and 4 bytes of data and code per instruction. In the Spectrum, it ran at 3.5 megahertz. So you had 3.5 million clock cycles, or as we generally call them, T-states. And the instructions take between 4 and 23 T-states per instruction. It was one of these computers where you have an accumulator. You don't have general registers like you might do on a 68000. So everything pretty much had to be done through the accumulator. You do all of your maths through the accumulator. We also have 3 16-bit registers that also work as 8-bit registers pairs. And what I mean by that is you have the 16-bit register pair called BC, but you can also access that as B and C 8-bit registers. So those are pretty flexible. And by convention, the register pairs had different usages. So the BC register pair was usually used as a 16-bit counter. You could also use it as an 8-bit counter. The DE register pair was generally used as a source register pair for copying. The the DE is destination, HL as source. We also have 2 index registers. So with an index register, you'd point at the start of a structure and then use fixed offsets to reference inside that structure. The index registers are pretty slow. You generally don't use them in games or demo coding. You might use them a little bit, but they're fairly slow instructions, so you try and avoid them. Then we have the kind of standard special registers that you'd have in any processor. We have a flags register, PC, program counter, stack pointer. There's only one stack pointer. Interrupt register, where you set up the interrupts. Refresh register, which is used for refreshing memory. You don't really use the I or R registers. They're just not important. So that's not a lot of registers. But you also have an entire alternate register set. So you have alternates for AF, BC, DE, and HL. And you can swap those in and out pretty cheaply. So that effectively gives you twice as many registers. And with any CPU, accessing code and data from registers is really quick. Accessing from memory is really slow. So a lot of your optimization is based around trying to keep as much in the registers as possible in your inner loops. For ROM, we have 2 16K ROMs. There's basic and, I'm going to use air quotes, operating system, because there wasn't much of an operating system in there. So it includes things like there's a floating point calculator stack, there's tape loading routines, there's simple drawing routines, there's a font. They're all really slow routines. And unfortunately for us, they're hardwired into memory, so they take up this bottom 16K of our address space. So they're not a lot of use. They're slow. They waste space. The only kind of place you might use them is something like this. This is a 256-byte demo I wrote. So I'm using the calculator stack to do the 3D maths, and I'm using the line drawing routines to draw the wireframes. It's pretty slow, but when you're using 256 bytes, you use whatever you can. So the ROM routines do have some use in size-limited demos. Next up is the video and the ULA. So the ULA is the chip that I talked about. That's the one custom chip. Its proper name is the uncommitted logic array. And it basically deals with the I/O between the processor and the rest of the system. So it deals with video, tape loading and saving, and keyboard. So its main job is generating the video display. You have a 50 hertz frame rate, and that generates a vertical blank interrupt. The only interrupt you have on the Spectrum is that one vertical blank interrupt. So it's only one interrupt, but it's kind of the most important one. You can synchronize your screen rendering with that. The video is generated straight from main memory. It's completely memory mapped. We have 2 video pages at different addresses, so we can do double buffering and write to those whilst the other one is showing. Then we get to the confusing bits. So the Spectrum has a 256 by 192 pixel resolution overall. That's the pixel resolution. So that's purely on and off pixels. Then on top of that, we have a 32 by 24 color resolution. So what that means is each one of these color resolution cells, or attributes as we call them, covers an 8 by 8 pixel space on the main screen. And in each one of those attribute cells, you can choose 2 colors. And that's the palette at the bottom, which was clearly not designed by an artist, clearly designed by a software engineer, because I love the Spectrum, but the palette is challenging. So what you could do, you could choose 2 colors for each cell. But of course, you couldn't choose any 2 colors. You could choose 2 from the top row of the dark colors or 2 from the bottom row for the bright colors. So you couldn't have, say, bright green and dark green in the same cell. You'd have to have bright green and dark blue. So it's a little bit hard to kind of visualize. So what that means in practice, this is the 256 by 192 pixel display. All you have is on and off pixels. This is then your 32 by 24 color attribute display. And when you overlay them on top of each other, you get an image. So you have your pixels, you have your attributes, and you have your final image. There are some advantages to this in that you can write to the pixel display without having to update the colors, or you can write to the colors without having to update the attributes. There is one last nasty trick up the sleeve of the Spectrum, which is how it actually generates video. I don't know whether you can hear that. That's the nasty sound of a Spectrum loading. So what you might expect is that it would load it linearly, one line at a time. As you can see, that's not what happens. It splits it up into 3 chunks, and then within each one of those chunks, it splits it up into 8 sub-chunks. It's a bit complicated, but what this basically means is when you're on one line on the screen, you can't simply step down to the next line. It's not a simple add 32 bytes on to go down a line. There's a formula, and there are a bunch of routines that will do this for you, but just be aware that you can't simply step down the screen lines. You have to think about how you code your graphics routines. What you generally do in practice is you build tables of the line addresses and just access those, rather than trying to calculate it. Despite all the limitations, there are some really nice graphics that people have done over the years. You'll spot the weird color palette, and it's something you get used to. Skin tones, there are no skin tones, so you have odd-looking skin colors. And these guys do a really good job of hiding that attribute grid. There's a lot of great stuff out there. So RAM. So the memory is arranged in 16K banks. So you can fit 4 of those. 16 times 4 is 64K, which is the full address space. So you can fit 4 banks in memory at once. We actually have 8 RAM banks, which gives you the full 128K. But you can only have 3 of those in memory on time, because the bottom one is taken up by ROM. There are some limited rules in how you can swap those in and out. But basically, you can't access the whole 128K at once. You have to page in and out the memory as you need it. The audio, again, the audio is pretty basic. It's pretty standard off-the-shelf stuff. It's a AY8912, which gives you 3 square wave channels, a mixer, and a noise generator. There is an envelope that you can share between all channels, but it's not particularly useful. Having said that, you get your standard chiptune style. You can hear that. You get your standard chiptune stuff out of it. And what you generally do is you run this on the vertical blank, so every 50th of a second you update the audio registers, and that's the kind of style you will get out of it. You can go further. You can update it more than 50 times a second. This is technique borrowed from the Atari ST world, where they have much better timers. So you can update more than 50 times a second very easily. On the Spectrum, you don't have the timers, so you have to cycle count. And the end result of that is you don't have a lot of CPU time left to do much else. So these guys here, they're just doing attribute effects in the background. They're just updating that attribute section of memory. It's nice effects, and the audio is great, but it's a real trade-off there. So let's talk about development tools. So the main things we need are, we need to write the code, we need to create the graphics, we need to create music, and we need to actually run and debug everything. So I'm just going to share a bunch of links now, and I'll share the slides afterwards so you can follow them up. Building the code, we'll go for generally just for an assembler. So there are a bunch of standard ones: Pasmo, Z80, ASM, SJASM Plus. There's also a thing called Z88DK, which is a C cross-compiler, which you can freely mix C and assembler. A lot of people are using that, writing some really good stuff with it. I don't know about demoscene, but certainly in the game world, people are using that quite heavily. It's an interesting one if you're If you just want to dip your toes in, you can write a lot of your stuff in C. There's also another one called Zeus, which is a full IDE. So you get an editor, a compiler, and a debugger and emulator in the same IDE. I generally use Pasmo. It's straightforward, it's simple, it works. And some resources quickly. Z80 Heaven is a great one for looking up Z80 code in general. There's a series of tutorials called How to Write ZX Spectrum games, which goes from the very basic. If you've got no knowledge of Z80, this is a good one to follow all the way through to actually writing a game. Also, look at resources for other computers that had Z80. MSX computers, Z80, it's a good resource. There's lots of resources out there for MSX. Obviously, we can't share the kind of graphics routines, but a lot of the algorithms are very similar. That's a good place to look. Graphics. So for graphics, there are some dedicated editors. Two of them that I know of are 7up and ZX Paintbrush, so they understand the limitations of a Spectrum, and you can paint directly. Also, if you're ever thinking about just converting graphics, I know nobody would ever think about just converting graphics, because it's cheating. But if you did want to do it, or if you wanted to kind of quickly test out some graphics, there's a good converter called Image to Spec. I've used that a few times just for testing stuff out. What I generally do when I'm doing graphics, well, generally I'll leave the graphics to the graphics person because they're much better at it. But if I need to do graphics, I will use Photoshop or Paint.net or something like that, draw it myself because I understand the limitations, and then I will use converter tools just to kind of convert that into the Spectrum format, not doing color conversion or anything like that. Music, there are a bunch of trackers around. Probably the easiest one is called Vortex Tracker 2, runs on Windows. It's quite nice. It's maybe slightly impenetrable to start with, but there are some good tutorials. There's a tutorial on chipmusic.org specifically for Vortex Tracker 2. And also, if you're interested in Spectrum music, there's a brilliant tutorial on YouTube by Gasman, who's one of the big sort of coders and musicians on the Spectrum scene. It's called Zero to Chiptune in 1 hour, where he takes from no knowledge of chiptunes on Spectrum through to writing a tune, and he does that as a seminar for an hour. That's really, really good kind of introduction to Spectrum music. So for running and debugging, there's a bunch of emulators. ZX Spin is what I generally use. There's also EmuZWin. EmuZWin is a really interesting one because it records every instruction, basically, so you can rewind time. This one's incredibly useful if you've got a crash that you can't track down, because basically what you do is you run your game or your demo until it crashes, and then you rewind, and then you can pick up the crash. That can be a real lifesaver. Spectaculator is quite a nice one. It's a paid-for one, or everything else is free. Fuse is also quite nice, and it's cross-platform. You may notice I just listed a bunch of emulators. To be completely honest, I can't remember the last time I ran any of my code on a real piece of hardware. The emulators are so good. If you do want to run stuff on hardware, get something like this. This is called a Divide. And what that is, it plugs into the back of your Spectrum. You put a compact flash card in it. This is standard amongst most other sort of 8-bit computers. And then it will emulate the tape routine, so you can load your demo or your game in a second rather than 5 minutes. These are, if you're testing on real hardware, this is the way to go. So let's start talking about a demo framework, what you need to write a demo. So there are lots of ways to write a demo on a Spectrum, and you're always going to have to try. There are always limitations you're fighting against, so there are different ways to do it. What works for me is we'll try and do 50 Hertz update, so full speed update. We'll use the double buffered screen to make that possible. We need a scripting system, so we can script the demo flow. We use Pasmo to assemble the code. We'll store the compressed data and resources in the spare memory banks and pull them into main memory as we need them. We'll write some utility in Python to package all the graphics and data together. And we'll use a makefile to glue everything together and sort out all the dependencies. So if you're going to write a demo, that's quite a sort of heavy amount of code to start with. So hopefully that's where I can come in and I've recently written a Z80, a ZX Spectrum demo framework, which got everything you need to start writing a demo. Comes with a bunch of sample effects. We'll cover some of those in the next few slides. It's currently in beta. If you're interested, just send me an email. I can share it with you and talk you through how it works. But the aim, again, here is to kind of bootstrap you. If you want to start writing Spectrum demos, and maybe you've written some Spectrum games, or you've written on demos on other platforms, this will give you all the basics you need to start writing Spectrum demos, and then you can kind of build on it from there. So let's start into coding some simple effects. So let's start with something ambitious. Let's start with full screen animation. So we're going to store some pictures of memory, copy to the screen. That will be easy. We have a bunch of memory, we have the screen, we copy from one to the other. That should be really straightforward. So we'll start with the first approach, the first naive approach. I'm going to kind of dive into some Z80 here, not too deeply, so don't worry too much. But essentially, the code on the left, we're going to point the HL register pair at our source graphics, DE at our screen address, which is memory mapped, BC is the amount of data we're going to copy, and then because it's a Z80 and we know we're supposed to do everything through the accumulator, we're going to do everything through the accumulator. So we load A with the first byte of source data, and then we store it into the first byte of destination. We point to the next source, next destination, decrease the counter, check if it's 0, and loop. That takes about 50 T-states per byte, and we've got, the screen is 6K, so that's 61,000 bytes. So that's going to take us about 300,000 T-states in total. Seems great. However, the Spectrum is running at 3.5 megahertz, and at 50 frames per second, that only gives us 70,000 T-states. So this simple naive approach is going to take us more than 4 frames. The Z80 is really underpowered when it comes to actually copying data. So that approach isn't going to work. So now we're going to start delving into some basic optimization. So the first thing we can try is unrolling. So rather than having a loop counter, we will just repeat that small byte, that small code that copies. We will repeat that 61,000 times. And that reduces the overhead of the loop. Now we're down to 26 T-states per byte. So that's almost half. It's still going to take us 160,000 T-states in total, so that's still over 2 frames. And because we've unrolled all that code, we've now used 24K of code to copy a screen in 2 frames. So it's still no good. We have to optimize further. Z80 has some block copy instructions, so we can try those. The main one is called LDIR. It's load, increment, repeat. So you do similar to what you did before. We point HL at the source, DE at the data, BC holds the screen size, and then we call this block copy instruction. And that takes 21 T-states per byte. It's quicker again, but we're still way over our target of 70,000. So we can try unrolling that. The LDIR uses a counter. There's another version which is LDI. So again, you're losing the overhead of the counter, and you're just unrolling it yourself. We're at 98,000. So we're still well over our 70,000 budget, and we've got 12K of code. So this is still unworkable. So what we get to now is kind of the proper way to do it, and that's using the stack. So I'm not going to write the code for this because it starts to get quite gnarly. But the pseudocode is, we point the stack at the source data, we pop the data from the stack into as many registers as we can, then we point the stack at the destination, and we push the data from the registers into the source destination. And we've got kind of 8 registers pairs free for this, so we can copy 16 bytes of data at a time. 16 bytes of data copied in 204 T-states. That works out as 12.75 T-states per byte. That's going to take us 78,000. We're still over our target, just over a frame, and we're using about 10K of code. It's kind of workable. We can work with that. So what do we do now? We can't copy an entire frame. So there are 2 options. We can drop to 25 hertz and update every other frame, but we don't want to do that because we want to run at 50 hertz because it looks better. So the other option is we reduce the amount we copy. So as a simple example, we can do just a static animation like this. So we have 6 frames of data stored in memory, and we copy them to the screen, and this is 50 hertz. It's not particularly exciting, but it's a start of what we can do. So then we ask the question, if we can copy about half a frame, what other things can we do? What about if we tried interlacing? So what about if we tried copying all of the even lines on one frame, and then all of the odd lines on another frame? And if we do that, we can start doing full screen animation. It's interlaced, so you've kind of lost half of the brightness, and you can see you can clearly see the interlacing, but it is possible to do full screen animation. And once you can do kind of full screen animation, we can start doing line picking based effects, a kind of staple of old school demo effects. So we can do full screen twister effects quite simply, and then you can extend to all the other line picking effects that are available. There is another possibility as well. This is, again, full screen, 50 hertz. And we're actually copying to every screen pixel, and to do that, we're reducing the amount of data we read, so we've got more time to write. So we use a small repeating pattern. So if we want to do full screen 50 hertz, we can do. We just have to reduce the amount of data that we're actually copying around. So what did we learn? The stack is absolutely the fastest way to copy data. You have to be a bit careful. Mainly, you have to be careful to run at 50 hertz. If you start creeping over that 50 hertz and you get the 50 hertz interrupt, then you will start writing rubbish data on your stack. So be careful with that. But that's fairly easy to avoid. The other one is unroll your inner loop code whenever you can. Those two are kind of the biggest optimization techniques you can get. And also, it is the classic trade-off between speed and size. We can make our code run faster by using more memory. It is as simple as that. So I said at the start that I had to cut a lot down. So this is going to be kind of more in note form. What else could we learn if we had more time? So one important one is don't worry too much about code and data size. We have a fair amount of code and data space available, and remember that all of our code and data that we're not using is going to be compressed in memory that's paged out. So we don't need to worry about that stuff so much. Keep everything you can in the registers. We touched on this earlier on. Register reads are fast, memory reads are slow. A lot of Z80 optimization comes from just keeping juggling everything in the registers. Unroll inner loop code whenever you can. I've already said this one, but I'm saying it again because it's massively important. When you unroll the code, it runs faster. You don't have the overhead of the loop counter, so that's faster from that point of view. And also, you have a spare register because you no longer need to have a loop counter. So unrolling is a huge technique. Aligning your tables on 256-byte boundaries. This helps massively with the way the Z80 accesses memory. If you remember those 16-byte registers that you had. So what you'll tend to do is you'll set the high byte to point at the base of a table, and then you can just set the low byte to look inside that table. So you end up with tables aligned on 256-byte boundaries that are 256 bytes long, and those are really quick to look up. So things like sign tables, line address tables, stick them in a 256-byte boundary, and they're much quicker to read. And the last one is more design related. It's design your effects to reduce the amount that you need to draw. So what do I mean by that? So here's a good example. There's a fair amount going on in this screen, so the code is non-trivial. But the key thing is, in the middle of the screen is a big static image. It looks great, but we're never updating that image, so we're saving ourselves a lot of time. Another more obvious example is this one, where we have a static image on the left-hand side and a twister effect on the right-hand side. So whilst it's full screen, we're actually only updating half the screen. And design is a great technique, a great way to get you out of a hole when you've not got enough time left. So you may notice as well in that effect there, the twister on the right-hand side of the screen is doing more than 2 colors in an attribute cell. So yes, you can break the color limits. Multicolor is possible. It requires very careful timing, and it doesn't leave much CPU time left for anything else. So on another 8 or 16-bit computer, you might have more interrupts. You might have a timer, or you might have a horizontal blank that you can use to time this. On a Spectrum, you can't. You have to cycle count. But effectively, what you're doing is, as the ULA is drawing the screen, as it draws past the line the first time, you then have to update the attributes before it draws it the next time. So you've got to be very quick, and you've got to be very cycle accurate. And you just have to cycle count. There's no other way around it. So again, this is sample code from the framework. It's not as pretty as the last example, but it's pretty basic, and it's exactly the same principle. So actually what we've got here is, rather than 2 colors within an 8x8 grid, we've got 4x4 colors. Again, you're kind of limited by the palette of the Spectrum. But there's sample code for this to show you how to do it. That's pretty much it. So hopefully this will kind of give you an idea of what's possible on the Spectrum. It will start you thinking about how you can use the stack to draw everything fast, and it really is a case of using the stack for everything, any copy operations. I've introduced a framework, so if anybody wants a framework to kind of bootstrap them, just talk to me and I can get you that, and it will include a bunch of demo effect sample code on how to do some basic examples like sprites, twisters, that kind of thing. Yeah, any questions?
Questions from her? Yes.
Yeah, hi. You mentioned the default, like the original like ROM that has like the tape load routines and that type of stuff, and said that it's not that great. Yeah, I mean, I've heard that there are some replacement ROMs, like the Gosh Wonderful ROM, which is, my understanding is that it's remarkably better than the original one. And my question really is that, are these allowed in demo competitions, and if they are, do they actually use them?
That's a good question. So you're talking about the existing ROMs are quite slow and quite poor. There are some replacement ROMs. I think there's a couple of efforts where people have cleanly reverse engineered the ROM and written replacements for it. Whilst I think they've tried to maintain the same entry points for all the key functions. So it's simply a drop-in replacement and pretty much everything should work. I don't know what the take-up of these is, to be honest. I think people, certainly in demo coding, people generally avoid using the ROM at all. So I don't know whether demo sceners are using them. Question whether it would be allowed. I don't see why not. The Spectrum scene is a little bit fractured as it is, because there's the original Sinclair Spectrums. There's also a lot of clones around that have different capabilities. So it's kind of in 2 parts. There's the original, there's a scene that concentrates on the 1 to 8K Spectrum, and then there's a whole other scene that concentrates on pretty much anything goes. I think as long as you're open and honest about what you're using, then yeah, people are happy to let you use it. I don't really have much experience with the ROMs myself, so I don't know, but yes, they exist and use them.
Okay, thank you.
Okay.
Any more questions from the audience? Okay.
Okay, so as you told us, there's like multiple different versions of the Spectrum, but were there any like successor, or what happened to the Sinclair? And because we don't really hear about them anymore. Okay,
so Sinclair was an interesting company. They were very innovative, and they produced a lot of stuff very cheaply. Before the ZX Spectrum, they released a computer called the ZX80, which was, I think, 1K. Before that, they produced some simple, like single-board programmable computers. So they had kind of a legacy of really simple stuff, and then the first ZX80, ZX81 kind of simple home computers. The Spectrum was really their best thing. After that, they brought out the Sinclair QL, which was meant to be more of a business machine. It was really weird in that it used a 68008. So you think 68,000, that's a lovely processor, but it was a 68,000 with a 16-bit address bus. So it's pretty useless. I think a couple of demos have come out for it, but nobody was really that bothered. At the end of the life cycle of the ZX Spectrum, Sinclair produced a couple of things that just bombed, completely bombed. And they were taken over by another company, Amstrad. And Amstrad kind of finished off the ZX Spectrum. It kind of reached its natural conclusion, and they didn't continue on with it. So the Spectrum pretty much died in '92. Recently, there have been a few reboots of it, where people are releasing their own hardware versions in FGPA or whatever. I think there are 2 or 3 different kind of modern versions of the Spectrum you can go out and buy today and just plug into your computer, put all the games and demos on, and I think probably plug a USB stick or something with the games in. So you can still buy them. I don't know how accurate they are. I think they are probably very accurate. The Spectrum is so simple that the emulators have uncovered all the secrets years ago. So emulation is pretty accurate. So I think the modern recreations in hardware are also pretty accurate. Does that answer your question?
Yes,
Okay.
Thank you.
So I have a question about the stack copying trick. Like, if I understood correctly, one instruction pushes and pops all registers, or can you specify what registers to push and pop and in what order, or are there many different push instructions for different sets of registers or something?
Okay, so the question is about stack copying. There isn't an instruction that pushes or pops everything. You push and pop register pairs at a time. So you can only push or pop a 16-bit register pair. So you can order them however you want. You can push as many or as few as you like. Yeah. Does that help?
Yeah, thanks.
Okay.
Any more? Yes.
Hi. First of all, thank you so much for a great talk. Much appreciated. My question is about, in general, kind of about the interleaving the synthesis of audio and the rendering of graphics. Mm-hmm. Is that something that you generally end up doing, like a lot manually, that you have to cycle count between like audio synthesis and graphics, or are there some techniques where you would be able to, like have the graphics code run first and then all of the audio synthesis code, or does it generally have to go very interleaved in this kind of manual fashion? So
are you talking about the Atarin demo where you had the more advanced audio, or just?
Kind of, yeah. So
yeah.
when you manual cycle counting for audio on the CPU.
Yes. Yeah, so normally when you're doing the audio, you just run it on the VBL and you just run your code. You don't need to cycle count or anything. When you're doing anything like multicolor or, as you say, the kind of more advanced audio where you want to update multiple times per frame, yes, you have to cycle count. There are no timers. There's no horizontal blank. There is no extra interrupts. So you just end up cycle counting. Cycle counting isn't that hard, and you don't have to be absolutely exact. There is a bit of play. But yeah, essentially you have to cycle count.
That or
sorry,
any good tooling to help for that, or is it just manual work that you do?
Whenever I've done it, I've only done multicolor, and it's literally a case of writing down the cycle counts, knowing how many cycles are in a line, and matching it. What you may have seen in some of those demos is I generally use border colors as a profiling tool. So you can set, as well as the main display, you can also set the border color. And what you can do is set the border color at certain instructions. So I would set the border color at the start of the first line and then change it at the second line. And then you can kind of see whether that's creeping left or right, whether it's creeping out of sync. So that helps quite heavily with that. There is another thing that I didn't go into here, which is contended memory, which is a whole other chapter. When the ULA is drawing the screen memory is contended because the ULA is trying to draw it and the Z80 is trying to read it. And the ULA wins out because it needs to. So sometimes the instructions that the Z80 is running get delayed very slightly whilst the screen has been drawing. If you're reading, the rule is if you're reading or writing from the screen memory whilst the screen is being drawn, you will get extra delay states inserted in your instructions. When the maths for that has been worked out and you can read the formulas for it, but whenever I've done it, I find it easier just to tune by eye, just by looking at it and just kind of counting the cycles, because it's really hard to keep track.
All right, thank you so much.
Okay.
Any more questions? Questions, comments? Here is one.
I was wondering that if you can do the animation frame under a frame, then why do you need a double buffering? Couldn't you just go on?
So the question is, why double buffer? Yes, you can. You can just write directly to the main frame. You've still got to be careful about how you write it, because obviously it's been rendered at the same time. So you've got to start at the right point and make sure you finish by the end. Otherwise, you'll get tearing on the screen as the screen is being rendered as you're changing the data. I generally find it easier to write to a second buffer and swap it, just because then you don't have to worry about the tearing. If you're copying an entire screen like we were there from top to bottom, then yes, a single buffer does work quite well. If you're doing something like a sprite effect or something like that, then obviously you've got to start sorting your sprites into the right order so that they're drawn in the right place on the screen so you don't get tearing. I suppose generally I just do stuff as double buffering. So that's, when I think about doing full screen, my first thought is I'll use a double buffer. But you're absolutely right. You could just use a single screen and that would then give you more memory. It's maybe a bit more advanced because you have to be careful about the tearing. But yeah. Does that help?
Any more questions? No? Paul, thank you so much.
Thank you.